Hello everyone, my name is Songjin Park, and I will be presenting from Team MATZOA. Today, our presentation is about comparing LSTM and transformer encoder models for the aging use text classification task. As our slogan says, a warm and insightful comparison served by Team MATZOA. We hope to make this comparison easy and enjoyable to understand. The task is simple. Given a short news text, the model classifies it into one of four categories: world, sports, business, and sci-tech. Transformer models are often considered stronger than LSTM models because they use self-attention, but aging news consists of relatively short use text. So our main question is, does the transformer still clearly out, outperform the LSTM? Our research questions are: first, transformer encoder process LSTM performance. Second, effect of max rank 64 to 128. To answer these questions, we conducted a main comparison and a overlation study. We used the aging news dataset from Hugging Face. It contains 120,000 training samples and 7,600 test samples. The dataset is class balanced across four classes. Since the official split only provides train the test set, we separate 10% of the training set as validation data. The final split is 108,000 samples has trained and validation have 12,000 samples and test have 7,600 samples. For pre-processing, we applied the sample pipeline to both models. This is important because we wanted to compare model structures, not pre-processing differences. The main settings are as follows. And we convert our text to lowercase, used a simple rule-based tokenizer, and built the vocabulary only from the training set. For tokenization, punctuation marks were removed or used as separators. For example, don't becomes don and t. Padding was handled differently for each model. Transformer used an attention mask to ignore padding. LSTM used the bandwidth length to select the finer non-padding hidden output. This prevents padding from affecting the sentence representation. First, the LSTM classifier. LSTM is the current model. It reads tokens one by one and updates its hidden state sequentially. So it is strong at running sequential patterns in text. The key idea is LSTM compresses the sentence sequentially into a finer hidden representation. Next, the transformer encoder. Unlike LSTM, transformer use self-attention. Self-attention allows each token to capture relationships with other tokens across the whole sentence. After the encoder, we use masked mean pooling to average only real token outputs. The key idea is transformer builds a sentence representation using self-attention. The main difference is simple. LSTM to recurrent model, and transformer to self-attention modeling. For a fair comparison, both models use similar setting, like embedding dimension is 128 and two-layer structure dropout is 0.2 and classifier has a linear classifier. So this experiment compares sequential modeling and self-attention modeling under similar conditions. The experiment has two parts. First, the main comparison, and second, the evaluation study. The common training setting as follows. Now let's look at the result. Under the max ranks 128 condition, the LSTM achieved test accuracy 1.9116 and test macro F1 1.9150. The transformer encoder achieved test accuracy 1.9138 and test macro F1 is 1.9137. So the transformer performed slightly better, but the difference was very small, only about 1.22 percentage points in test accuracy. This means transformer had a small advantage, but LSTM was still competitive. The biggest confusion occurred between business and sci-tech. This happened because many samples contained overlapping topics, such as technology, companies, software markets, stock movements, and telecommunications. These topics can sound like both business and sci-tech. So the main error was not only caused by model weakness, it was also caused by semantic overlap between labels. The LSTM training loss decreased faster and became lower, but its validation loss increased after epoch 3, showing mild repeating. In contrast, the transformer had higher training loss, but its validation loss decreased more stably. So lower training loss does not always mean better test performance. Generalization is more important. Now, the second question is, does increasing max ranks from 64 to 128 improve performance? For LSTM, improved slightly, while for the transformer, max ranks 64 was better. The best model was transformer encoder with max ranks 64. So longer sequence length does not always improve performance. The ovulation loss curves shows the similar pattern. All models were optimized successfully, but LSTM models showed stronger repeating signs. Transformer models shows more stable validation trends. So the key message is the best sequence length depends on the data set and model. For this task, max rank 64 was enough for the transformer. Both models classify sports most accurately. This is because sports articles contain clearly keywords such as team name, players, and matches. However, business and sci-tech were more difficult. The number of misclassified samples was LSTM has 672. Transformer encoders had 655. The transformer made few errors, but the gap was not large. There were three main error cases. First, both models failed when business and sci-tech overlapped. For example, an inter-product delay article was labeled business, but both models predict sci-tech. Second, only LSTM failed when later words changed the context. For example, in a Kobe Bryant article, legal words effort the LSTM prediction. Third, only transfer failed when financial or numerical tokens effort mean pooling. So each model fails for a different reason. To summarize, there are these main conclusions. First, transfer encoder performed slightly better than LSTM, but the gap was small. Second, increasing sequence length did not always improve performance. The best result came from transformer max length 64. Third, the main error source was the semantic overlap between business and sci-tech. Final message. Transformer encoder was generally more effective than LSTM. However, the performance difference was small. Longer sequence lengths did not always guarantee better performance. Business and sci-tech overlap was the main source of misclassification. That concludes my presentation. Thank you.